angle less than this angle. So force will have a more effect towards y-axis, right? Hafiz?
Yes, sir.
I need response from you. Then only I will know whether you understood or not. Okay. So you answer to me because this is your doubt. So this force component in y-axis will be more. Okay. In that case, this mission 53. So naturally, this one, see, initially this angle was theta. Agreed?
Yes, sir.
This is the force F.
Yes, sir.
P has X component X, isn't it? This is X. Agreed?
Yes, sir.
It is a Y component that we can mark here. This is Y component, isn't it?
Yes, sir.
Square root of X squared plus Y squared will give you R. This is a position vector R. If you want magnitude of this, you will take square root of X squared plus Y squared. So this is the mathematics side of it. Now here, due to this Y component, this can resolve into two component, Fy, Fx. This is Fy, this is Fx. Since this angle is less, this component is more. So naturally, P will shift to this point, isn't it? There's a rotation. Agreed?
Yes, sir.
When it is shifting, okay, this is the direction it is shifting. So now new position of this R is this. This is a new position. Now P shifting to this point, isn't it?
Yes, sir.
When P shifting to this new point, what happened to X? X decreased, right?
Yes, sir.
X became, see, X decreased, sorry. X decreased to a new position, right?
Yes,
this
sir.
is now new value of X. Now this is called dx, right?
Small change.
Small change, dx or delta x. Small change is called dx. Agreed?
Yes, sir.
Tomorrow onwards, last entry, 5 minutes. Okay, only 5 minutes I'll take attendance. 3 minutes before I will start the attendance. 5 minutes after the class I will take, because it's too difficult every day, wasting a lot of time. So if you enter in between, I have to stop the class. I have to mark your attendance, and it's coming back. It's wasting time. So I will allow you, but I will not give you attendance. Okay, I'll mark attendance. I will not mark attendance. I will put absent. That's all. Clear? So 3 minutes before I will start entry. 5 minutes after this. Clear? We cannot take more than that time. Those are coming late, I'll permit, but no attendance permitted. Okay, now this is theta, isn't it?
Yes, sir.
So here x, now this is moving from P to P dash. Now what happened? X shifted to x1. That means this displacement is dx, isn't it?
Yes, sir.
At the same time, what happened to y? Y become y dash now. So this displacement is dy, isn't it?
Yes, sir.
So what exactly happened here? P directly displaced to P dash, right?
Yes, sir.
Look at this, what is happening here exactly. P directly shifted to P dash, right? That is called small displacement dr. Okay? Agreed?
Yes, sir.
Now, according to triangular law, look here, R plus, that means OP is R plus this point, dr is equal to this one, R plus dr, new position, triangular law, isn't it? See, this is one side of the vector, this is another side of the vector, resultant is in the opposite side, isn't it?
Yes, sir.
Sir, what is dr here?
dr.
Yes, sir. What is dr?
When x is shifting to x1, y is shifting to y1, then
Yes.
r is shifting to
RX.
the position, right? So that displacement is dr.
Yes, sir. Yes, sir.
Is it clear?
Yes, sir. Yes, sir. It's clear now.
Now in this point, you see this much distance is dx, right?
Yes, sir.
This much distance is dy,
DY.
isn't it?
Yes, sir.
So root of dx square plus dy square, if you're taking, you will get dr also.
Yes, sir.
Agreed? Now,
Yes, sir.
in the when this is going p to p dash, theta increasing by d theta, isn't it?
Yes, sir.
So suppose this is an Hafiz doubt. Look, dx by dt means what? Rate of change of position, right?
Yes, sir.
Yes,
That
sir.
will give velocity.
Change of position with respect to time. That is velocity. Agreed?
Yes. Yes, sir.
Yes.
Acceleration means d by dt of velocity, rate of change of velocity.
Yes.
That means change in velocity with respect to time. That means small change in small time. That's what differentiation, right?
Yes, sir.
Yes, sir.
Yes, sir.
Because in a continuously varying, motion, we cannot take total displacement, total v by total t. So in this case, small portion only will study. You see, dv by dt will give you acceleration of this region. dv by dt will give you acceleration of this region. This studies is known as differentiation actually. Agreed?
Yes, sir.
Yes, sir.
So in the derivation is question dx by d theta. That means when theta shifting to d theta, how much dx changing? That's the meaning of it. Did you get it, Hafiz?
Yes.
Yes, sir.
If it's not clear, tell me. That meaning of this, we are studying dx, x is equal to r cos theta. Okay, now dx by d theta means what is the value of x? What is the value of x? Change in x.
Yes.
When theta changing to d theta. Theta increasing by d theta, how much x changing? That's what dx by d theta meaning. So r into minus sine theta. This is a new value of dx by d theta. Is it clear?
Yes, sir.
So if you want dx, you can calculate. Dx is equal to minus r sine theta d theta. See, minus sign shows it is decreasing, right?
Yes, sir.
How much angle? Suppose if this is 30 degree, substitute 30 degree here. If it is increase 1 degree, that 1 degree multiply here. That's the meaning of it. Clear?
Yes, sir.
Now we are coming to our regular topic. 57. So today total saying 56. What was the topic yesterday? We were doing moment of inertia, right?
Yes.
Yes, sir.
Moment of inertia. Okay. So moment of inertia. Next one, radius of gyration. Radius of gyration.
Sir, we didn't finish the definition of moment of inertia of rigid body.
Yes, sir.
There is no definition. Okay, right. Let M1, M2, M3, Mn are the particles, are the masses of the particles, are the masses of the particle which constitute the entire body, which constitute the entire body. And R1, R2, dot. R1, R2, dot, Rn are their perpendicular distances. Perpendicular, see this is M1 and this is M2, this is M3. Are their perpendicular distances? Are their perpendicular distances from the axis of rotation? From the axis of rotation. Then moment of inertia of the entire body can be written as moment of inertia of the entire body can be written as moment of inertia of the entire body can be written as m1 r1 squared plus m2 r2 squared plus dot 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 mn rn squared. If you want, you can draw diagram for it. This is the axis of rotation, and this is say m1, this is r1. Say this is m2, this is r2. Like that, large number of bodies we can imagine here, mn rn. This can also be written as I sigma. Sigma means add all these things. MIRI squared. Here I is equal to 1 to n. Is it over?
Yes, sir.
सर एक मिनट उसके बाद chat में.
Can I continue?
Yes sir. Yes sir.
Next heading, radius of gyration. Radius of gyration. Gyration. Radius of gyration. Look here. See, here theoretically we are saying this big rigid body consists of M1, M2, M3, M4, M. How many particles we will count? Billions and billions of particles are there that constitute the body, isn't it? Suppose molecules or atoms, if you consider itself, very large number, getting their mass and measuring their perpendicular distances, theoretically we can speak, but practically not possible. But we have another alternative technique to overcome this difficulty. We know the entire mass of the body is focused at center of mass, right?
Yes, sir.
So if you
Yes, sir.
consider center of mass, all this m1 plus m2 plus m3 plus dot 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 mn is focused at one point. Clear? So instead of considering m1, m2, m3, consider one point that is center of mass and draw a perpendicular distance from axis of rotation to that center of mass. So entire body has a mass capital M, and this is K, perpendicular distance to center of mass. Now, with respect to this, calculate moment of inertia. I is equal to mk squared, total mass into perpendicular distance to center of mass. This will be equal to moment of inertia calculated as sum of moment of inertia of individual particles. Is it clear?
Yes sir. Yes sir.
Sir.
First, we are assuming this particle consists of M1, M2, M3, M4, large number of particles. Just imagine. And if you are adding, we are saying we will get total moment of inertia. But practically counting that many numbers is not possible. Measuring perpendicular distance also not possible. So what we are assuming, the entire mass, M1 plus M2 plus M3, if you are adding, all these masses come to one point. That is center of mass, isn't it?
Yes sir. Yes sir.
Yes, sir.
That means the entire body, just imagine it is comprised to a single point, that is center of mass. And measure distance from axis of rotation to that center of mass. That is K. Now you take mk squared. This answer will be same as sum of, see, m1 r1 plus m2, this one, sum of these individual particles. Sum of moment of inertia of individual particles. This K value is known as radius of gyration. So radius of gyration is the perpendicular distance of the center of mass from axis of rotation, with which the moment of inertia of the body calculated is equal to the moment of inertia of the entire body calculated as sum of moment of inertia of individual particles. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Radius of gyration. Radius of gyration K. Radius of gyration K is the perpendicular distance from the axis of rotation. Radius of gyration K is the perpendicular distance from axis of rotation to the center of mass of the body.
Sir, can you repeat it again, sir, please?
See, you must write in a continuous flow because, you know, I'm just from my memory, I'm speaking. So if I miss it, then sentence will change. So I will repeat, be along with me, okay? Then after that,
Yes,
you ask me. At least one person will complete, we can read it out.
Still there. It will be there in the chat.
Roll number 32. Roll number 32.
Yes, sir.
Why are you so late? So I will not give you attendance, okay? It's not just passing through the class. It is attend. Look here. Again, I'm repeating, listen carefully, okay? Don't break in between, don't pull me back. Then sentences will confuse. Right. Radius of gyration K, radius of gyration K is the perpendicular distance, is the perpendicular distance from the axis of rotation to center of mass. From the axis of rotation to center of mass of the object. From the axis of rotation to the center of mass of the object. With which the moment of inertia calculated, bracket I is equal to mk squared. I is equal to mk squared, with which the moment of inertia calculated, bracket I is equal to mk squared.
Sir, M capital.
Capital. With which the moment of inertia calculated is equal to the moment of inertia of the body is equal to the moment of inertia of the body is equal to the moment of inertia of the body calculated as moment of inertia of the body calculated as sum, SUM, see this way, sum, moment of inertia of the body calculated as sum of the moment of inertia, the sum of moment of inertia of the individual particles, see m1 r1 squared, m2 r squared, m3 r squared, like that, sum of moment of inertia of individual particles, sum of moment of inertia of the individual particle which constitute that body, Any doubt?
No, sir.
Yes, it's clear, right?
Yes, sir. Yes, sir.
So this is just theoretical approach. This is the practical approach. Okay. Now roll number 76. Are you there?
Yes, sir.
I won't give you attendance for last 10 minutes. Okay. Before, just after the class, only 5 minutes attendance time. After that, if you
Sir, is it possible that in the case of radius of gyration, the K can be 0 as center of mass can be at the point of axis only?
No, we won't keep the axis at the center of mass. We can keep axis anywhere, right?
Yes, sir.
So we will keep axis away from center of mass somewhere here. Then we will get K value, right?
Okay, sir.
So moment of inertia with respect to this point only you will get.
Okay, sir.
But if you want moment of inertia keep changing. If you're keeping at the axis, moment of inertia will be different. In that case, we cannot say moment of inertia 0, but we cannot use this formula.
Okay, sir.
Clear? For this, there is another formula we have to study. Clear?
Yes, sir.
So on the through the center of mass, this axis is going. This formula we cannot apply because K value will be 0. Then we cannot
Yes,
say
sir.
moment of inertia 0. For that, there are another formulas we have to develop. Clear?
Yes, sir.
Next one. Kinetic energy of a rotating body. Kinetic energy of a rotating body, or rotational kinetic energy also we can say. Kinetic energy of a rotating body. Kinetic energy of a rotating body. What is the kinetic energy of a body traveling along straight line?
Half mv
Half
squared.
mv
Half
squared.
mv squared, isn't it? I
Yes,
told
sir.
you, in linear motion, mass decides inertia. But in rotational motion, moment of inertia decides inertia, isn't it? mr squared.
Yes, sir.
Agree?
Yes, sir. Yes, sir.
So here, in linear motion, kinetic energy formula is half mv squared. Therefore, in rotational motion, kinetic energy formula will be, instead of m, we have to write I. Instead of v, we have to write
Omega.
angular speed, omega squared, right?
Yes, sir.
This is what we are going to prove. So like this, you must be able to relate physical quantities in linear motion and physical quantities in rotational motion. So that you must know what physical quantity plays same role in rotational motion. So for example, linear displacement, similar role in rotational motion, angular displacement, theta.
Theta.
Linear velocity, angular velocity. Linear acceleration, angular acceleration.
Alpha.
Force, torque. Linear momentum, angular momentum. Inertia, moment of inertia.
Moment of inertia.
See, it's interesting, right?
Yes,
So
sir.
similarly, kinetic energy, rotational kinetic energy. That's what. So here M we can replace by I because they are analogous property. It's called analogous. Like this, one more question will be asked. Which physical quantity in rotation motion is analogous to mass in linear motion? So moment of inertia.
Moment of inertia.
What is the role mass plays in linear motion? Same role moment of inertia plays in rotational motion. Is it clear?
Yes, sir.
Yes,
Now
sir.
this one we are going to prove. Kinetic energy half mv square omega squared. We have to prove it. But okay. Look how we are going to prove it. This is a rigid body. Okay. This is the axis of rotation here. Axis of rotation. This is angular speed. We know angular speed of every particle will be same, isn't it? You remember?
Yes, sir.
Yes, sir.
Yes, sir.
For example, I told you this example. This is a circular motion. You're all standing in this line. Okay, this is first person, this is second person, and this is the third person. Say 1, 2, 3. I told you, you all have to cover one rotation without breaking the line. That means all will have same angular speed. But the person in the first point has to just walk. He has to just having a jogging. But the last person has to run to maintain the line, isn't it?
Yes, sir.
Yes,
So
sir.
they all have same angular speed, but this has more linear speed. Or another example, suppose this is a metal body, keep rotating. From here, if a piece broken, that will go straight away, far distance. Here it will fall less distance. Here it will fall less distance because this linear velocity is larger. So these are all examples we studied and we got a formula. V is equal to R omega.
R omega.
As distance increasing from center, linear velocity will increase, isn't it?
Yes, sir.
See, why we are playing discus throw, right? In the sports, Those are having little long arm, they can exert more force than a person having little short arm. That's why these taller people and all, they can easily do that. Okay, look here now. So this is rotation motion. That will be same for all the particles. Now we are marking here some particle example. Okay, look, this is M1 particle, M1. Okay, so while it is rotating, M1 is going which direction? Inward, right? Like this. Can you see? While it is rotating, here if it breaks, that will go this way, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
So if the same body, if it come this side, particle will have outward, right? Velocity.
Yes, sir.
This side it will have velocity this way. This side it will
Yes,
have
sir.
velocity this way. That means a tangent will give you velocity all around, isn't it?
Yes, sir.
So this particle, we have velocity inward. Inward means we have to mark a cross here. Because which is going inward, we can show only by cross. You understood?
Yes, sir. Yes,
Yes,
sir.
See, for
sir.
example, this pen I'm keeping this way. You are seeing the back side, right?
Yes, sir.
Yes, sir.
That is marked as cross. But here you are seeing the tip. That is dot. Isn't it?
So, sir, because it is going inward, can we say it's going in clockwise motion?
Anti-clockwise. It's rotating this way, right? According to the diagram, it's rotating like this. So M1 is going anti-clockwise, inward. You keep a clock
Oh, okay, okay.
horizontal. Isn't it?
Yes, sir.
Oh. So same body while reaching here, it will come outward, right?
Yes, sir.
Yes, sir.
So if this is a particle that is M2, for example, this is another particle M2. While M1 is going inward with the velocity V1, this will come outward with the velocity V2, isn't it? This is 90 degree.
Yes, sir.
Yes, sir.
Agreed? Now
Yes,
another
sir.
particle M3 may be going inside now. All these side particles are going inward according to the diagram. This is now M3. Okay, and velocity, it is inward. That is V3. Now here there may be another particle. This is coming outward again, isn't it? See, it's coming outward with a velocity V4, particle M4. This is R4, this is R1, this is R3, this is R2. Like that, Mn number of particles we can mark, isn't it?
Yes, sir.
Yes, sir.
Now, kinetic energy of the first particle